All right. Then another thing that we take for granted, and the idea here is that the struggle isn't between religion and science. The struggle is between religion and materialism. And what I mean by materialism is not the way we use it today, like love of money. He's a materialistic person, he loves money. What I mean by materialism is the philosophy of materialism, that nothing exists except matter, energy, and the laws of physics and randomness. That there's no guiding intellect behind this creation. That is the philosophical materialism. And the point that gets missed is that 300 years ago, 400 years ago, on the surface of things, the world looked much more like what the materialists believed it looked like. And what the people of religion said seemed to make no scientific sense. And we are very lucky that we live at a time when science has advanced to the point that the more science advances, it actually seems that the view of religion is more compatible with science than the view of materialism. For the longest time, materialists sort of hijacked science. That if you were going to be logical, you were philosophically a materialist. And that religion was the purview of the primitive, the irrational, the people who couldn't explain the world, couldn't explain creation, so they had to come up with a creation myth. They had to invent, astaghfirullah, a God to explain why we're here. So it was the primitives who needed religion. The science of the last couple of centuries, particularly actually the last 50 years, has upended that. And it has shown that the world is much more similar in scientific terms to what the people of religion have been saying rather than what the materialists have been saying for 2 millennia. And again, there are things that I don't want us to take for granted. And so let's go back here. إِنَّ فِي خَلْقِ السَّمَاوَاتِ وَالْأَرْضِ. In the creation of the heavens and the earth, there are signs for those endowed with insight. This is making a statement that the heavens and the earth were created. We, because we live in the age of the Big Bang, take that for granted. Because science and religion have now come to the same conclusion that the universe had a beginning. We need to take a big picture view. This was revolutionary because for more than 2,000 years, that wasn't the scientific understanding. If you were a credible scientist, you did not believe that the universe was created. From the time of Aristotle, the universe was thought to be perfect and unchanging. It had always been there, and it would always be there, always the same. And all scientists essentially believed that. In fact, the famous quote by Laplace, who was a scientist during Napoleon's time, when Napoleon asked him, Laplace was a famous mathematician and physicist, and Napoleon asked him, why does God not figure in any of your theories? And Laplace replied, sir, I have no need of that hypothesis, astaghfirullah, that he had no need of the hypothesis of a creator. So this is a philosophical issue that I don't want us to miss. The Qur'an talks about the creation. وَمَا خَلَقْنَا السَّمَاوَاتِ وَالْأَرْضَ وَمَا بَيْنَهُمَا لَاعِبِينَ. We did not create this merely an idle sport. مَا خَلَقْنَاهُمَا إِلَّا بِالْحَقِّ وَلَكِنَّ أَكْثَرَهُمْ لَا يَعْلَمُونَ. We did not create them except with an inner truth, but most of them do not understand. And so we need to understand just how revolutionary it was for the Bible to talk about in the beginning, that there was a beginning, the opening words of Genesis. How revolutionary it was on scientific grounds for the Qur'an to say that the heavens and the earth were created. Here again is Newton's law of gravitation, right? So Newton comes up with this, and that's why he's Newton, right? That's his amazing discovery. But there was a problem. Newton could explain how gravity worked, and he could explain how fast an apple would fall and hit the ground, and how fast the moon cycles the earth, and we can now calculate the rise of the hilal, and we calculate the orbits of all of the planets, and it is based on this that we could actually send somebody up to the moon, and the rocket ship didn't miss the moon, you knew where the moon was going to be, and so on. But Newton couldn't explain how gravity worked. Why was there gravity? He could explain, do the calculations, but why does gravity exist? Why does the sun exert a gravitational force on the earth? Why should that be? He had no explanation for that, and he recognized that he had no explanation for that. Who was the man who explained that? It was Albert Einstein, with yet another theory that superseded Newton's, and that is the theory of general relativity. And he said gravity is nothing more than the curvature of space, that heavy, massive objects make space curve. Like if you have, the analogy that's always used is, imagine stretching a rubber sheet or a bed sheet, and you roll a marble across the surface of that sheet, it'll just roll. Now you put a bowling ball on there, and you roll the marble, and the bowling ball curves the sheet, and the marble will then curve around the bowling ball. And so that gravity is really the curvature of space-time. And in the remaining time, I'll talk a lot about the theory of general relativity. And it's basically a geometrical theory of gravitation. And it unifies special relativity and Newton's law of universal gravitation, and basically says that gravitation isn't due to a force, but it's a manifestation of curvature of space and time, and that this curvature is produced by mass energy. Things that have mass and energy curve space-time. And Einstein formulated something known as the field equations that we will get to, and to explain just how this works. And later we'll talk in more detail, but I just want to put the slide up on the board. These are what is known as the Einstein equations. These are the equations of general relativity, and later I'll explain why I call them equations when all you're seeing up here is one equation. And I know that this isn't a typical topic in mosques, okay, to put up the equation of general relativity, but I think as Muslims we should have some familiarity. Not all of us, are going to be theoretical physicists and understand in detail how this works, but we also should know something about it. These components on the left talk about the curvature of space and time, and think about what I'm saying here. Time curves. Okay, what does that even mean? These components on the right talk about the mass and the energy that cause space and time to curve. And so basically mass tells space-time how to curve, and curved space-time tells mass how to move, and you put it all together and you get an explanation of gravitation. Now, it took Einstein, people say it took Einstein 10 whole years to derive the equations of general relativity. As I've tried to study and understand these equations, I say, not it took Einstein 10 whole years, I say, my gosh, it took Einstein only 10 years to come up with this. It is truly remarkable. I mean, it's an unbelievable leap of intelligence that this happened, and people in the know think that if you were to rank the intellectual achievements of humanity, of people's minds, that this is the single greatest intellectual triumph that humans have come up with to understand this. But remember, an equation is different than a solution. I could tell you that something is governed by the equation that x plus y equals 10. That's the equation. And that this is the valid law of physics, x plus y equals 10. Then you can come up with solutions. And you can say, well, x is 9 and y is 1, then x plus y equals 10, that's a valid solution. But x is 5 and y is 12, that's not valid. Then if I say, well, it's actually not one equation, it's two equations, it's x plus y equals 10 and x minus y equals 2, now instead of an infinite number of valid solutions, I now only have one valid solution. That x has to be 6 and y has to be 4. Okay, and that's the only solution that works, but it's a solution, it's the solution to the equations. Einstein didn't come up with a solution. He came up with the equations. He said nature is described by this series of equations. Soon after he published the equations, a couple of people came up with solutions, which in and of itself was very unexpected. A physicist named Friedman came up with something known as the Friedman solution. A Dutch physicist named Willem de Sitter came up with a solution. And it turned out, much to Einstein's dismay, and I'm quoting here Professor Leo Sartori, so that this isn't my interpretation of things. To his dismay, Einstein found that the field equations of general relativity for his model have no static solutions. What does that mean? It means that Einstein, as brilliant a mind as he was, like every scientist for 2,000 years before, believed that the universe was static. It didn't change. His equations, the solutions, all said the universe was changing. It either had to be contracting or expanding. It couldn't just be as it is. And this was very, very bothersome to him. Again, another physics book by Stephen Barr, The Realization that the Universe Must Be Dynamic, profoundly disturbed Einstein. He had naturally assumed that the universe must be static and eternal. So now this was a problem, because Einstein had found equations that he believed to be correct, but these equations said the universe has to be either expanding or contracting. And Einstein, as brilliant a mind as he was, as much as he was able to think outside the box, he couldn't think outside this box. So, and Sir Arthur Eddington said, the notion of a beginning is repugnant to me. And Arthur Eddington was the physicist who helped prove that general relativity was correct. One of the amazing predictions of general relativity is that gravity bends light. That's, again, very counterintuitive. We all know that light travels in straight lines. It doesn't bend. That's why we can't see around a corner, because if light bent, I could see you if you stood around the corner. I can hear you if you're around the corner and you yell, I'll hear you, but I can't see you. I actually have to go so that I have what they call a line of sight, right? Shooters and snipers, shouldn't talk about that in a mosque, right? They need a line of sight, okay? Because light travels in straight lines. Well, Einstein said, no, gravity bends light. Arthur Eddington led the expedition that during a solar eclipse proved that starlight bends around the sun, that gravity, massive bodies that exert gravity do bend light. And it was this discovery, by the way, in 1919 that propelled Einstein immediately to a world celebrity. Before that, he was a wonk tinkering away at, publishing in Annalen der Physik, and, who is this guy? Except among physicists, but the world certainly didn't know this man, even though his discoveries were profound. But once this hit the press, Einstein became a celebrity. And people interviewed Eddington. So Eddington was a huge deal. Eddington was one of the very few people that actually could understand Einstein's equations. And so a reporter asked him, he said, Sir Arthur, is it true that only two people in the world understand the general theory of relativity, or the theory of general relativity? And Eddington stayed silent. And the reporter said, come on, Eddington, don't be modest. And Eddington said, no, not at all. I'm just trying to think who the third person is. Did I mess that up? The beginning of that should have been, The reporter asked him, there are only 3 people in the world who understand relativity. I think I messed it up. So the reporter asked, is it true that there are only 3 people in the world that understand relativity? Eddington didn't answer, and then he said, don't be modest, and then Eddington said, I'm just trying to think who the 3rd person is. That's how hard general relativity is to understand. But even these very, very brilliant people did not believe that the universe was dynamic. It had to be static. So what does Einstein do? He goes back to his equations, and he inserts this term. Compare this equation to this equation. Einstein throws this in. This is known as the cosmological constant. And there are good physical reasons that this is allowed. There's a reason that this can be here. For any of the engineers or what have you, or people in the room, it's because the derivative of this has to equal 0. And if this is a constant, when you take the derivative of a constant goes to 0. So if that made no sense, don't worry about it. But to address the scientists in the room, it wasn't just quackery. I mean, mathematically, it's still okay. So he puts in this cosmological constant. And the reason he puts in the cosmological constant is because he realized that, okay, the solutions are saying that the gravitation would pull all matter together. Just like the Earth attracts the sun, all of the matter in the universe would attract itself to itself, and the universe would be collapsing, and the only way that could be countered is if something was pushing out and the universe was expanding. But it couldn't be static. It couldn't just sit there. But this cosmological constant exerted an anti-gravity force, so that it would be just enough to balance the gravitational attraction of the stars to each other and make the universe static. So he inserts in this cosmological constant so that the universe could be static as he believed it had to be. Okay? This is now, we're talking 1917, 1918, 1919. Then in 1929, 10 years later, Edwin Hubble, the man after whom the Hubble telescope is named, makes an amazing discovery. And Hubble's discovery is that the universe is expanding. And this was on empirical grounds, by observation. He looked at the galaxies that are near to us and far away from us and realized that the universe is expanding and that the galaxies that are closest to us are moving away from us a little bit more slowly, and that the galaxies that are far away from us are moving away from us at a very rapid rate, and it obeys a law of physics, and that the universe is expanding. This discovery was absolutely revolutionary. Einstein was wrong. And Stephen Hawking, whom you all know, said that the discovery of the expansion of the universe was one of the great intellectual revolutions of the 20th century. It came as a total surprise and changed the discussion of the origin of the universe. At that point, Einstein went back and he said that putting in this cosmological constant, he called it the greatest blunder of his life. He said this was the biggest mistake of my life. Why? Because if he had just trusted his equations, he could have predicted that the universe was expanding 10 years before Hubble made that discovery, on purely theoretical grounds. The equations were right there and telling him, but he just didn't want to believe it. Okay? Now, where does that go? Well, what are the implications? If the universe is expanding, then if you play that tape backward at a certain time, the galaxies were closer than they are now, because it's expanding. So they had to expand to get here. If you go backward, they were closer together. If you go backward more, they were closer together. If you go backward more and more and more, there's a certain point where they were all together, and that is the point of the Big Bang. So if you follow the expansion backward, that led to another very startling result of modern cosmology, the notion of the Big Bang. We take the idea of the Big Bang for granted because we have grown up with it. This is not to be taken for granted. This was a revolution in science. Nobody believed that this could be possible. And in fact, the whole term Big Bang, which was coined by Fred Hoyle in the 1950s, was a pejorative and derogatory term. he was saying to his interviewer, you really expect us to believe in something that the universe began as a Big Bang? He was saying this is ludicrous. And yet, it turned out that so it was. And Stephen Hawking said, Roger Penrose and I were able to show that Einstein's general theory of relativity implied that the universe and time itself must have had a beginning in a tremendous explosion. And so, contrary to the belief of all of scientists up until our modern age, the universe did have a beginning. There was a moment of creation. Now, the debate is, was this creation divine or was it not divine? But that's a separate issue, which scientists, materialists, I shouldn't say scientists, materialists gloss over. That their understanding of a static and unchanging universe that had no beginning was entirely wrong. And the view of religionists that there was a beginning to this universe, that there was a moment of creation, turns out to be scientifically the correct interpretation and understanding of the laws of physics given by Einstein's equations. Okay, let me just give you a moment to breathe because, as I said, we're going to try to kind of have this be academic. I want to just give you a glimpse of what these equations are or what they mean. And of course, I'm not really qualified to do that. This is a year-long course in graduate level physics. But at least we should just feel that we've seen something about it. This most startling discovery of the 20th century, or one of the two most startling discoveries. I'm sorry? No. These are the Einstein equations.
The c to the power 4 on the right side?
Yeah, thank you. The c to the power 4 is just what's called a dimensionality constant to make the units work out right. But because it's a constant, a lot of physicists drop it because it's just, it's just to make the dimensions come out right. But yes, you're absolutely right. We should divide it by c to the 4th, c being the speed of light. Okay? This here is what is known as the Ricci tensor. The Ricci tensor is a measure of how much space curves. And what is this idea that space can curve? Well, we can think about a two-dimensional analogy. If space is flat, the way everybody thought it was flat, including Newton, then it's like this surface of this table. And it's a two-dimensional space. There's a dimension this way and that way. But if I were to take this tablecloth and form it into the surface of a sphere, and I don't want you to think about a three-dimensional sphere, but just the surface, okay? What is on the surface of the sphere, it would still be the same two-dimensional thing, but now I've made it curved. So that is the curvature of space. And all of the laws of geometry that we learn have to be changed when you're dealing in curved space. Young people here, has anybody studied the Pythagorean theorem? Any young people? Pythagorean theorem? A squared plus b squared equals c squared in a right triangle? Or what is the sum of the angles of a triangle? Some young person tell me, I want to feel I'm not the only person awake. Angles 180, right? If you were to draw that same, young person, wonderful, God bless. If you were to draw that triangle on the surface of a sphere, if you just bring a globe and draw the triangle on a globe and measure the angles, they don't add up to 180. Okay? Angles of a triangle add up to 180 only in flat space. So things change when you're dealing with curved space than flat space. The Ricci tensor measures the curvature of space, and the curvature is also specified by this term here, which is known as the metric tensor. The Ricci tensor is an equation that involves products and partial derivatives of something else known as the connection coefficient or the Christoffel symbol. And the Christoffel symbol, give me just 2-3 minutes. If this makes no sense, don't worry about it in the least. But has to do with how you take the derivative of something called a tensor in physics. And so this Ricci tensor is a mixture of derivatives and products of Christoffel symbols. And the Christoffel symbol itself is a mixture of products and derivatives of the metric tensor that specifies the curvature of space. So inside each one of these is this equation, and inside each one of these terms is this equation. So they're all folded into each other and compactified to make it look like something non-threatening. In fact, it's something very, very threatening. U and V are the coordinates of space and time, and there are 4 of them. 0 for time, and the 3 dimensions of space, x, y, and z, length, height, and width. So U can assume 4 from 0 to 3, V can assume 4, so there are actually 16 then of these equations. If you take a look at all the possible combinations, I could have R00, R01, R02, R12, R13, so there would be 16 of these terms. This thing here on the right is known as the stress energy momentum tensor, and it also has 16 terms. And it measures all of the different types of mass and energy and pressure and stress that could be in the universe. So all forms of energy affect all forms of space curvature. And because there are 16 of these different indices, there are 16 equations. And because of certain symmetries in this matrix, that 1, 0 equals 0, 1, if you actually count up 2, 0 equals 0, 2, so UV equals VU, there would be 10 separate individual ones. So the Einstein equations are 10 separate equations that are partial differential equations which are nonlinear. Is there anybody here who has solved differential equations? Differential equations can be solved, but we usually solve ordinary linear differential equations. When they become partial differential equations, that's very hard. When they become nonlinear partial differential equations, that's essentially impossible. When they become not one equation, like x plus y is 10, that has a lot of solutions. But when I couple it to another equation and I say x plus y is 10, but x minus y is 2, now I restrict the solutions. So when I get 10 of these solutions, and something has to be true for all 10, nonlinear partial differential equations, it's essentially impossible. Okay, so that's why this discovery was so remarkable. It's nearly incomprehensible to understand when somebody's trying to teach it to you. To think that somebody derived it from scratch. Nobody was explaining it to them. They had to think through it and say, this is how the universe works. It recalls to me, one of mathematician was talking about a fellow mathematician, and he said he's an extraordinary genius. And the guy said, oh, okay, that's great. He said, no, you don't understand. There are 2 types of geniuses. There's the ordinary genius, and the ordinary genius is the person that you and I could be like if only we were many times better. But the extraordinary genius is the sort of person that even if we were many times better, we couldn't be like them. Meaning that if Einstein was an ordinary genius, then I could say, okay, it took Einstein 10 years to derive this. I could do it in 100 because he was a genius, but I'm not a genius. So okay, fine. But Einstein was an extraordinary genius. Trying to understand these equations, I've realized that if you had given me 1,000 years or 10,000 years, there's no way I could have ever come up with this, no matter what. And that's, so, and these, of course, do we now take Newton's laws and flush them down the toilet? Forgive me. Because Einstein came up with the theory of gravitation. I mean, we know Newton's laws works. We use them to get people to the moon, and we use them to calculate the orbits of the planets, and Newton was hailed as a genius. So these look nothing like Newton's equations. So what do we do with that? Well, one entire branch of this study is to show that with the right assumptions, meaning fairly weak gravity and low speeds, these equations actually do reduce to Newton's theory of gravity. So Newton's theory of gravity turns out to be a special case in flat space of Einstein's equations. And you can show that, and Newton's law of force, F equals ma, mass times acceleration. Acceleration is the second derivative of position. You can see here that there's one derivative in the Ricci tensor, and then this Christoffel symbol itself has a derivative of the metric tensor. So the derivative of this, which also has a derivative, is the second derivative. Okay, so there is a way to show that Einstein's equations under the low gravity, low speed world in which we live do reduce to Newton's theory of gravity. So it's not like they're irreconcilable, and Einstein understood very well that one of the tests of the correctness of his theory of general relativity is that it had to reduce to Newton's theory. If it disagreed with Newton, then it must have been wrong. And so this is just a diagram of the idea of the bending of light. And this was what was shown by Eddington in 1919, that gravity does bend light. And here's a picture of Einstein posing with his field equations. And here's the Time magazine cover that named Einstein Person of the Century at the close of the 20th century. And I think that was really no understatement. Between the special theory and the general theory and the photoelectric effect, this man was really an extraordinary genius. Einstein, in fact, made another prediction, and he said that if his theory is correct, there would have to be something known as gravity waves, ripples in space-time, that gravitational disturbances send a ripple. Because as you know, when he came up with his theory of special relativity, one of the consequences was that nothing could travel faster than the speed of light. With Newton's law of gravitation that says here's the law that describes the gravitational force between the Earth and the Sun, one of the consequences of Newton's laws was that if I make the Sun disappear, all of a sudden that gravitational attraction would stop. So the Earth, instead of moving in a circle or an ellipse, forgive me, would immediately fly off its orbit, just like the, what do we call this thing, the sling? The thing that David used against Goliath? Yeah, you spin a slingshot. You spin it around your head. I thought this was a slingshot. Anyway, this thing that you spin around your head and you let go and the rock flies out, so that if the Sun disappeared, the Earth would immediately start moving in a straight line off its orbit. What does that mean? It means that I could send you a message on Earth instantaneously if I could make the Sun disappear, then I could send you a message by saying, when the Earth starts to fly off its orbit, you'll know that I'm here. And that would be instantaneous. As soon as the Sun disappears, the Earth would start to fly off its orbit. That's a problem. It's a problem for special relativity because it means that signal, that information, traveled faster than the speed of light. How long does it take light to get from the Sun to the Earth? 8 minutes. Good. Who said that? Wonderful. 8 minutes. Excellent. So, no signal should be able to travel from the Sun to the Earth faster than 8 minutes. If Newton's laws were correct, I could send you a signal faster than 8 minutes. I could make the Sun disappear and the Earth would change its orbit, and that would happen instantaneously. For that to not happen, a disturbance in the fabric of space-time that travels at the speed of light has to occur. And it would take 8 minutes for the Earth to realize that the Sun has moved off its orbit. The fabric of space-time that makes the Earth revolve around the Sun would take 8 minutes to change. These are known as gravity waves. For the longest time, even though it was predicted, they could not be detected. We did not have the precision instruments to detect them. Finally, LIGO, the Laser Interferometer Gravitational Wave Observatory, in 2015, this article was published in 2016, but in late 2015, gravity waves, as predicted by Einstein, were detected. 100 years after the general theory of relativity, the theory of general relativity was published. So his insight was amazing, and this was sort of one of the final tests awaiting verification, and it was indeed. So where does all this take us? Let's get back to what we were talking about in terms of religion, the resistance to the beginning. Even though Einstein's theories showed then that there had to be a Big Bang in which the universe began, even in the late 1950s, this is from an article called How Cosmology Became a Science in Scientific American, into the late 1950s, 2/3 of leading American astronomers and physicists believed the universe had no beginning. Even then, even into the 50s. Now we live in an age where all scientists believe in the Big Bang in the beginning, showing that the vision that the people of religion had was correct. And there's even a joke about it. That, you know, the men of science took 2,000 years to climb the mountain of knowledge in regards to this notion that the universe had a beginning, and when they got up to the top, they found the people of religion there at the top already. Okay? That we knew the universe had a beginning. And so, إن في خلق السماوات والأرض واختلاف الليل والنهار لآيات لأولي الألباب. When we look, we really can discover. And when Genesis says, in the beginning, God created the heavens and the earth, it is beginning to look more like that than what the materialists used to believe. Why did it take so long for scientists to accept the Big Bang? Well, revolutionary ideas, ideas that are earth-shaking, take a long time to be accepted. And that goes to show you how revolutionary the idea of a beginning, which we as Muslims and Christians and Jews accepted at face value, was for the world of science. There's a lot of neat scientific evidence for it. This is a picture known as the cosmic microwave background radiation. These are, the line is the curve that is the theoretical prediction if our current understanding of the universe is correct. The dots are the measured radiation, and you see how closely the measurements agree with the theory. So this curve was predicted by Gamow in 1948, and then these measurements were made later as this cosmic microwave background was discovered in 1965. How can I tell you what imagine if you have an electric stove and you turn on the eye and you know that it glows red, then you turn off the stove and then the eye cools off and becomes dark again, but you know that it's still going to stay hot for a while. If you were to touch it, you would burn your finger, okay? And that's one of the dangers of electric stoves. Little kids think that it's off and they put their hand away. Yes, it's off, but it still hasn't cooled down. That's because it's still radiating, but it's in the infrared. We can't see it, okay? But that radiation has a spectrum. And if you think of an explosion like the Big Bang that was red hot, like the red hot eye of your stove, after 15 billion years, it will cool off, but there will still be some residual heat or residual radiation. And that has something known as the black body spectrum, and this is what it's predicted, and this is what it's measured. When this was measured, this is essentially a lock that the Big Bang had to have occurred. Nothing else could produce this cosmic microwave background radiation throughout the universe. If the universe was static and eternal, there wouldn't be this low level of very, very subtle temperature radiation that follows this black body curve. That's why Penzias and Wilson won a Nobel Prize when they discovered the cosmic microwave background radiation. It was predicted back in 48, discovered in 65. And it's actually a funny story because they were radio astronomers and they were interested in something else entirely, and they kept hearing this low-level hiss in their equipment. They said, what the heck is doing this? Why are we getting this interference? And they looked at all their equipment and all their setting and all the interferometers and the resistors and nothing. And then somebody had the bright idea that, you know what, maybe it's pigeon droppings in the astronomical dish. So they went out to the dish to check for pigeon droppings. And there were no pigeon droppings. And then finally they met another scientist at Princeton who was telling them, hey, you know, something about the theory of microwave background. Say, oh my gosh, this is what our radio antenna is showing. We've discovered the microwave background radiation, and they won the Nobel Prize for it. Okay, so that's why we believe the Big Bang is true. So again, science, why is science important to faith? It teaches us what seems to be real often is not. It's often a surface illusion. And that's the quote I put up before from Brian Greene.